Hello everyone, welcome back to the channel. I am Dr. Vikrant Yadav, Assistant Professor in Department of Mathematics, School of CS and AI at SR University, Warangal. In today's lecture, we are going to discuss one of the most powerful and widely used numerical technique, the Newton-Raphson method. Now, before we go deeper, let me ask you a simple question. What do we do when an equation cannot be solved easily using algebraic methods, or when finding exact roots becomes very difficult? In such cases, we use numerical methods, and among them, the Newton-Raphson method is one of the fastest and most efficient techniques to approximate roots. This method is based on a very interesting idea. It uses tangent lines to get closer and closer to the actual root of the equation. So, in this video, we will understand what is Newton's Raphson method, the mathematical formula behind it, and how it works step by step. Okay? And in the upcoming parts, we'll also solve examples for better understanding. By the end of this lecture, you will be able to apply this method confidently to solve nonlinear equations. So stay with me till the end, and if you find this video helpful, don't forget to like, share and subscribe to the channel. So let's get started. Now let us move ahead and understand the Newton-Raphson method in detail. First, let me ask you a simple question. What do we actually mean by solving an equation like f of x equal to 0? In many cases, especially in real-world problems, equations are not simple. Okay, they may be non-linear, may be complicated, or even impossible to solve using basic algebra. So, what to do in such situations? We use numerical methods, okay, in such situations, and one of the most powerful methods among them is Newton-Raphson method. Now let us understand the definition of Newton-Raphson method. This method is an iterative root finding algorithm. Okay, this is an iterative root finding algorithm. What does iterative mean here? It means we do not get the root or answer in one step. Instead, we start with an initial guess and then we improve that guess step by step. Each step takes us closer to the actual root of the equation. Now, here comes the most interesting part. Okay, this method actually uses tangent line of the curve. So instead of directly solving the equation, we use a geometrical idea. Let us imagine you have a curve representing the function that is f of x. You pick a point on that curve, your initial guess, okay? At that point, you draw a tangent line. Say in the figure you can see the point is x naught. The value of the function at that point is fx naught, okay? So you picked up that point, and at that point you draw the tangent line. Now, instead of following the curve, you follow the tangent line and see where it cuts the x-axis. That point becomes the new or next approximation. In the figure it is x1. Okay, why do we use this method actually? Okay, we'll try to get the meaning of it. There are four main or major reasons behind this. The first one is its very fast convergence. The Newton-Raphson method has something called quadratic convergence. And now What does that mean? It means that we are close to the root. If we are close, it means once we are close to the root, the method becomes extremely fast. Okay, each step significantly improves the accuracy. So compared to many other numerical methods, this one is much faster. Again, it requires only basic information, that is f of x and f prime x. Okay, the function f(x) and its derivative f prime x. That's it. So you can differentiate the function and you can easily apply this method then. It has got widely used applications. Okay, this method is not just theoretical, it is used in engineering problems, scientific computations, optimization techniques, machine learning algorithms, and physics simulations, and so and so. Okay, so learning this method is very useful practically. Also, it is foundation of many algorithms. In fact, many advanced numerical techniques are based on the Newton-Raphson idea. So if you understand this method well, you will build up a strong foundation in numerical analysis. Now, what is the key idea of this method? Now, let us focus on the core idea because this is the heart of this method. At each step in this method, we replace the actual value by its tangent line. Okay, actual curve by its tangent line. Okay, let's go step by step. Suppose your current guess is x naught, this point. Okay, current guess is x naught. You draw a tangent line to the curve and then you extend that tangent line. Okay, where does the tangent line meet the x-axis? Okay, this line meets the x-axis at x1. Let us say. So this x1 will be your next approximation. Now again at x1, this point x1, you draw the tangent at this point now, x1 fx1. Then where it cuts the x-axis, it is x2, say. Okay, then you just draw a tangent at the point x2 fx2. Okay, and find where it cuts the x-axis. Okay, this gives the point x3, and the process continues step by step, getting closer and closer to the actual root. Okay, let me explain this with in very simple words. Instead of following a curved path, we follow a straight line approximation here. Okay, and since straight lines are easier to handle, we can quickly reach the solution. But one thing you should remember, the method works very well when the initial guess is close to the root. Okay, if the guess is too far, sometimes the method may converge slowly or even fail. So choosing a good starting point is very important. Okay, choosing a good starting point is very important. So let us continue to the next slide. Now let us move to the most important part of this method, that is derivation of the iteration formula. Okay, this is where actual mathematics comes in, and once you understand this, the entire method becomes very clear. Let us assume that we already have a current approximation, say xn. Okay, the current approximation is xn. Now remember what we discussed earlier. At this point, we draw a tangent line to the curve y equal to fx. So our curve is y equal to fx, and we need to draw a tangent at this point xn. Okay, so the point on the curve is xn fxn. That is very simple to understand, right? Now, equation of tangent line we need to find out next. So from basic calculus, we know that the equation of tangent line at a point is this one, at a point, okay? And the slope is this one. So let me pull out the equation again. Y minus fxn equal to f prime xn into x minus xn. This is the equation of a line that is basically tangent line only at the point xn comma fxn. Okay, and this is a very standard formula. Here f prime xn is the slope of the tangent and xn is our current approximation. Now here comes the main idea of the Newton-Raphson method. We are interested in finding the root, right? That means we want the point where y equal to 0. Okay, here we want the point where y equals to 0. You can say this point y equal to 0. So what do? We simply put y equal to 0 in this equation. Okay, we're going to put y equal to 0 in this equation, and then when we substitute y equal to 0 in this equation, we are getting xn plus 1, this formula. Xn plus 1 equal to xn minus fxn upon f prime xn. Okay. Therefore, the next approximation is xn plus 1. Now, let us understand what this formula actually means. This formula tells us how to move from current guess xn to xn plus 1, okay, to the next guess xn plus 1. Let us break it. Fxn tells us this fxn tells us how far we are from 0, okay. F prime xn, the denominator ratio, okay, tells the slope of the curve, and the ratio adjusts the correction step. So essentially we are correcting our guess using slope information. Okay. Now one very important condition is that here this part f prime xn should not be 0. It should be non-zero, because if the derivative becomes 0, the formula will not work. That is obvious, okay? Because division by 0 will occur. So always ensure that the derivative is non-zero at the approximation point. Okay. Now, the next question is, when do we stop the iteration? We cannot continue for infinity, right? So we use stopping criteria. There are mainly three common conditions. First one is if the difference between the successive values is very small, that is xn plus 1 minus xn is less than epsilon, where epsilon is very small. In that case, we will stop the iterations. Next is the value of the function becomes very small at the xn plus 1th iteration or any iteration, okay, any approximated value actually. Then we stop, or the relative error is small. That is equal to, here it is relative error, okay, relative error E and epsilon s. This ensure these three conditions basically ensure that we stop when we have reached a sufficiently accurate solution. Okay, either of these conditions or maybe more will ensure that we have reached a sufficiently accurate solution. Okay, now let us discuss one of the most powerful features of this method, the order of convergence. Okay, Newton-Raphson method has quadratic convergence, which is order 2. Okay, quadratic means order 2. That is, error at the n plus 1th approximation will be approximately equal to f double derivative at the point alpha upon 2 times f prime alpha, and this is error at the nth approximation. Its square is there. Okay, what does this mean actually? The error gets squared at each step. So it is, if the error is small, it becomes much smaller very quickly. That is the point here. Okay. In simple words, the number of correct digits roughly doubles at each iteration. Okay. Now, this is why Newton-Raphson method is much faster than methods like bisection method, which has only linear convergence, order 1. Right? So we have derived the iteration formula, we have understood how it works, okay, and learned when to stop and seen why it is so fast. Okay, so now let us continue to the next slide. Now that we have understood the formula of Newton-Raphson method, let us see how to actually apply it step by step. In other words, we are now converting the formula into an algorithm. Okay, this is exactly how you will solve problems in exams or programming. First step is to define the function. Okay, first step is very simple. For define the function f of x and compute the derivative fx and f prime x. This is very important because the entire method depends on function's value and its slope, that is the derivative f prime x. So make sure you correctly calculate the derivative. Then step 2 is choosing initial guess. Okay, so choose an initial guess, say x naught. Okay, now this step is very crucial actually. Your guess, your guess should be close to the actual root, and that is reasonable and logical because a good initial guess leads to faster convergence, and a poor guess may lead to wrong results or failure even. And third step is tolerance and iterations. Now we define stopping conditions here. Okay, choose tolerance, that is epsilon, how accurate you want the answer to be, that is tolerance, and maximum number of iterations, that is equal to capital N. Okay, so this ensures that the process stops when accuracy is achieved or stops after a certain number of steps. Okay, and step 4, that is the iteration process or the core part of this method that comes. Okay, then we repeat the following steps in this iteration process. First is compute function's value at the current guess xn. Okay, compute the values of function, that is f of xn and f prime xn. These two values you need to calculate. Then in this step, okay, then 4.2 steps is checking derivative condition. It means that f prime x should not be equal to 0. F prime xn actually should not be equal to 0 for that guess xn. If it is 0, stop immediately because division by 0 would lead to the failure. Okay, that is not possible. So the method will fail in this case if f prime xn is 0. Okay. In the next step, we are having how to apply the iteration formula. We compute the next approximation x n plus 1 equal to xn minus fxn over f prime xn. This is the main working formula and this is very important, okay? Each iteration improves the accuracy, correct? With this formula. Now, we check this stopping condition, okay? We check that is the difference small enough. This checking criteria, this stopping criteria, we check two conditions: whether the difference is small enough, okay, or difference of the iterations, that approximation xn xn plus 1 that way, or is the function's value small, it is very small, it's close to 0, okay. If yes, then we stop the process, okay. If the stopping condition is satisfied, then accept the x and the root equal to x n plus 1th value. This value will be the root, okay, and the value of the function is f x n plus 1, okay, at that approximation x n plus 1. Finally, this confirms the accuracy of the solution. Means which one confirms the accuracy of the solution? The root and the corresponding function value. Okay. Now we'll see when does this method fail. Okay. This discussion is really important. When does Newton-Raphson method fail? There are several situations here. Okay. First is this f prime xn is 0 at any step, then the method will fail. Second is if the initial guess is far from the root, then the method may diverge or may fail. Okay, may not give the correct result. Then, if the function has an inflection point near the root, inflection point, okay, that we study in maxima and minima, point of inflection, okay, that if it is there, then convergence becomes unstable. Next point is if multiple roots are very close, the method may behave unpredictably. Okay, then roots may not be predicted correctly. So always be careful by choosing the starting point. Okay. Now, what are the conditions for success of this method? For this method to work properly, the following should hold. Okay, without fail, that the function is differentiable and the derivative is not zero near the root, and the initial guess should be close to the actual root. Okay, should be close to the actual root. So these are the conditions. I hope these conditions you understood very well. Okay, now let us move to the next slide. Now let us move to the most important part of this lecture, solved example. Okay, because this is where you will actually understand how to apply the method step by step. We are given in the problem that the function is x cube minus x minus 2, and we are asked to find a root starting with x not equal to 1.5, this value x not equal to 1.5. Okay, first we write the function and its derivative. This is function and this is the derivative. Derivative of x cube minus x minus 2 is simple. It is 3x square minus 1. Okay. Now we can write the Newton-Raphson formula. That is here xn plus 1 equals to xn minus the function's value upon its derivative's value. Okay. So you can see the formula and initial guess x naught equals to 1.5. Now let us calculate the iteration step by step. If the value of n is 0, this n is 0, so xn is basically 1.5 only. This xn corresponding to this iteration is 1.5. Okay. Then the value of the function at that point is 0.875 and value of derivative at this point is 5.75. Okay. Now apply the formula x1 equal to 1.5. The formula here will be x1 equal to this x naught, that is 1.5, minus 0 point value of the function, that is 875, divided by the derivatives value, that is 5.75. Okay, so we calculated the iteration number in this x1, and that value comes out to be this one. Okay, 1.3478, right? So that is your value x1. This is x1's value. Okay. Now after that you calculate the value of the function from this. This is 0.1006 and derivate the value of f prime xn is 4.4495. All these values are calculating. You are calculating with the help of calculators because manual calculation will become difficult. Okay. Similar way you calculated x2 here, this. Okay, x2, and that value is this one, 1.3252. Similar way you are calculating fxn or fx2. This is your fx2. This is f prime x2. Okay. Next is iteration number 4. That is x4. Sorry, this will be x3. Okay. This gives you x0, this gives you x1, this gives you x2, this gives you x3. That's it. Okay. So these steps are same. Now, after 3 iterations, we now observe something very important. Okay. The value of the function, the xn, the approximation of the root. This is 3, 4 here. It is 3, 2, 3, 2. Okay. So this should be correct up to 4 decimal places, right? So the difference is very small in this case because it is 5 to here, it is 4, 7. In the next step, it will be much lower. Okay, this means we are very close to the root. So the final answer that we can conclude with is root this one, x equal to approximately equal to 1.3247, right? Now we can verify this as well. If we substitute back this value f of 1.3247, okay, and solve it, then we will approximately get approximately, okay, not real, approximately get 0.0001, okay, that is approximately to be equal to 0 only. Okay, since the value is very close to 0, our answer is correct. I hope you are getting this. Okay. Now let us take another very interesting example, finding the square root of number using Newton-Raphson method. Okay. In this problem, we are asked to compute root 5, the value of the number root 5. Okay. So now remember, Newton-Raphson method works for equations of the form f of x equal to 0. Okay. So here the equation will become x square minus 5 equal to 0. Correct. So because this root 5 is the root of the equation x square minus 5 equal to 0 only, right? Because it will be x equal to 5, x square equal to 5. And when we will take the square root, it will become x equal to root 5. Okay, so our function is this one, f of x equal to x square minus 5, derivative is f prime x equal to 2x. Now apply the Newton's Raphson formula. This is x n plus 1 equal to xn equal to xn square minus 5, that is the function itself, upon its derivative. Okay, so we have separated it like xn over 2 and 5 over 2xn. And this formula is also known as classical Babylonian formula for square roots. That is some other term. Okay, next is the time to just calculate the iterations step by step. Okay, so our initial guess is here x not equal to 2 actually. This is initial guess is x not equal to 2. So this is reasonable because initial guess we are taking y, because one is 2 number, another is 3. Its square is 4, its square is 9. So that means root 5 will lie very close to only, so our initial guess is 2 here. Okay, so in iteration number 1, that is n equal to 0, initial guess is 2, this is your x naught, this is x1, this is x2, and these values are fx naught, this is fx1, okay, no, not this one, these are the values of the this iteration formula, right? This xn plus 1, this is xn, okay, these are the iterations, right? So after 3 iterations, we are getting the value as 2.2361. Okay, so this is very close value. Okay, so our iteration we can stop here actually. So now observe that x1 is 2.25, this is 2.23, this is 2.2361. So the root repeated actually. The value of xn plus 1 is repeated value. Okay. So there is the value is no longer changing. This means the method has converged after third iteration. Okay, so we conclude that the value of root 5 is actually equal to 2 point is approximately, basically using a Newton-Raphson method, is approximately equal to 2.2361. Okay, and also we can compare it with the true value. Okay, value of root 5, that is equal to 2.2367607. Okay, and the error will come out to be very less, that is the error equal to this one, less than 0.001, 0001. Okay, I hope you enjoyed this lecture. If you found this video helpful, don't forget to like, share and subscribe to the channel. Thank you.